Good evening, everyone. Thanks for joining and sorry for the inconvenience. So today, let us, we have some suggestions from our attendees last time. So one of them is, this is the first question we'll be taking up from GATE 2020. Then the other topics that were suggested were shear center and reinforced concrete design and matrix method of structural analysis. So let us look at them one by one. So this question, what is it? Layout blank. Okay. So this is an interesting question in structural analysis. And it's a very it should be done very carefully. It's easy to make mistakes in this question. So let us see how to solve this. So joints I, J, K, L, Q, and M of the given frame are pin connected. So these joints, let me put a pin in these joints. So I, J, K, L, Q, M, they are all pin connected. R and so we should be very careful. These are pin connected, which means the members framing at that joint are connected by pins. They are free to rotate about that. Continuous members JM and KQ are connected through a pin at point P. So these are continuous members connected with a pin. So this is not pin connected. So it's not free. The members as a whole are free to rotate, but the joint itself is not a pin joint. So that is another type of pin. And the frame has got hinge supports at joints R and S. So this is a different type of support. So here we have a hinge support. Here we have continuous members connected with a pin like a scissor. And here we have actual pin connected joint. And then the loading conditions are given. And also, so we are asked to find out the reaction, horizontal reaction at the support S. So you had asked me if this problem can be solved with the method of sections, and the answer is no, because it is a frame structure. In method of, you know how the method of section works, right? So if you have something, method of section works if you make such a cut that it exposes only it exposes at most 3 unknowns at a time, right? So if you have truss members, the direction of the force is known, and also and it is also known that the shear forces, and it doesn't transmit any bending moments or shear forces. So when you make a cut, so how the method of sections works, because you make a cut, you take one of the resulting bodies and you establish equilibrium onto that body. That is how the method of sections works. But how many equations of equilibrium we have for for a planar body? We have 3 equations of equilibrium, which means to have some meaningful solution, you have to expose only 3 unknowns. But this is a frame structure, which means if you say, suppose you take a section here, how many unknowns this, let me not draw the rest, but if you see, it has an axial force, it has a shear force, it has a bending moment. And similar to this member, this has an axial force, shear force, and a bending moment. So you cannot solve this by the method of sections. That is the thing. Yeah. But I guess where you would have got that is I checked the solution on the GATE portal. One of the students, yeah, so that is extremely incorrect. I should say it is incorrect. I remember what he has done is he made a cut here and then exposed the unknowns here, and he assumed that the forces are axial. But the problem is this is a frame. This is not a truss. And if it is a truss, this is unstable. So that is incorrect. And you have continuous. So the funny thing is here he had mentioned that this has 0 axial force and this has got some other axial force or so. But that's not correct, right? That is in general not correct. So maybe I can write to NPTEL that maybe that has to be reviewed again. But so no problem. That's not the correct approach. The correct approach is they should be treated as frame unless anything else is stated. So actually another issue with the question is what people have assumed at this point. So we'll look at it also. So this is what happens when we are not careful with the assumptions. So let me draw a better view of these. So the joints I, J, L, K are pin connected. So this looks something like you have a pin and you have another member connected here. And this is a continuous member, so this extends here. So it is something like a scissor. And a scissor bends when you try to cut something very hard, right? So it is not an axial force member. It is not a truss member. So you have something like this. So it is something like this. And this is pin connected. This is pin connected. So this is a continuous member. Yeah, the angles are a little uh, and this is a scissor type connection. You have a midpoint. Same thing. So you have a pin. And then what about this point? Explicitly mentioned I, J, K, L, Q are pin connected, but they didn't mention that R and S are pin connected. So unless otherwise it is stated explicitly, you need to treat them as moment resisting connections, right? That is how we treat frames as. So this is a continuous member. So this, the end, these are continuous. That is, this angle is 90, whatever, 90 degrees, right? So this is 1 in 1. So this is 45 degrees. So this is 90 degrees, which means unless it deforms, that remains at 90 degrees. Or during deformation also, that is what it means if it's a moment resisting connection. But the member as such can be hinged here. That is what it means. So the last two, the last one on both sides, the connection, if you draw in reality, it is something. It is some V-shaped structure, V-shaped frame, which is pinned to some support, but the angle of the V itself cannot change. This is the two arms of the V are not pin connected. This remains rigid. So if you see this problem, first let us see if it is statically. Again, most of the solutions that I found online by the coaching center, say Time or MEDC or all of them, or this test, all of them, they have made another mistake. So first thing, let us try to solve. Let us try to go step by step. So this is actually a difficult problem, and I think the answer key gives 15. That is also probably incorrect because of unsaid assumptions. So given, let me put this is R, I, J, K, S, M, L, Q, L, Q, and M, and then N and P. So determine if it is statically determinate or indeterminate. So what is the degree of static indeterminacy? Static indeterminacy. So how do you find out for a frames? So if you take every arm has got one. So every arm has got three internal forces, right? So the bending moment, shear force, and axial force in are the unknowns in this member. Similarly, so how many? So treat these two as two different members, but they are connected rigidly, right? So let us find out the members. How many members we have? We have 1, 2. These two are continuous. So 3, 4, 5, 6, 7, and 8. So the number of members we have, right? A number of reactions. The number of reactions we have are 1, 2. So this is spin. So vertical and horizontal reactions. Here vertical and horizontal reactions. It is the pin. So there are like this. It is pinned here. And for simplicity, let us say we are supporting the scissor with something. Right? So if you look at this is actually statically determinate structure. The reason is that if you take the unknown, this is, let us take this as one member, this as one member. So you have two members, but two members are free to deform themselves, right? They have some force which is holding them together, which is the pin force. Pin force has two components. It doesn't transmit any movement, but it has got two components. If you draw the free body diagram of both, right? This is one arm, this is one other arm of the scissor. You need to put the reactions 1, 2, 3, 4, and you have the pin force, equal and opposite pin force. So there are two of force coming from the pin connection. So there are unknown forces which are holding these two together. So those finding the static indeterminacy. So from the pins, you have two pins. So you have two pins. Now, what does it contribute to the unknowns? So 8 into 3, you have 24 24 unknowns in the members. And reactions, how many we have? And we have 4 reactions, so that comes directly. You have 4 unknown reactions. We have 2, and each pin has 2 unknown forces, so you have 4. So the total number of unknowns in this problem is 32. So it looks solvable. It is very difficult, but it's not the case. You can do a lot of simplifying steps. And how many equations we have? How many equations of equilibrium we have? For every, we can write 3 equations, right? For yes.
3
For
equilibrium
every
equations.
member, so there are. You can draw the free body diagram. So for each member, you have 3 equilibrium equations. So you get 3 equilibrium equations. That is fine. So 24. And how many internal hinges we have? You have 1, 2, 3, 4, 5, and 6. So we have internal hinges. We have 6 internal hinges. And what is the condition at internal hinges? How many equations we get from internal hinges? Each hinge has 0 bending moment. So that you have one equation about every hinge. Whenever you draw the free body diagram, to the fact that the individual members have to be in equilibrium, you know bending moment in the member at the point of connection has to be 0. So that is one additional known. That is one additional known detail. So so this gives 6 equations of equilibrium. Anything else? No. So I have 30 equations. So I have 32 unknowns and 30 equations. Your static indeterminacy is actually 2. So does this approach? So I hope you agree with this. There is nothing we have missed out. So this is a statical structure to the second degree, and this cannot be this can be solved by the stiffness method, probability method. So if you use the method of undetermined method of consistent deformations, you draw a redundant structure and then draw the primary structure, expose the redundant forces, and then you can do it. There are 2x2 system of equations, and then the unknowns system for the unknown forces. So that is how you solve this. So that is the long way. So let us see what are the different things we can do to simplify such a problem in structural analysis. Right. So in this problem, let me redraw this with the forces. So we have something like this. Right. So we have a hinge. We have a hinge support. So this is the difference. So when you have continuous members connected by a pin, it is something like a scissor. This obviously resists some bending moment. If you draw the bending moment of this inclined member, it will look something like this. Bending moment, there will be shear force. So it's not right to say it actual. When you have a pin connection like this, then the case is different. You can say the bending moment is 0 at the point of the. But this is something like an intermediate support. So the bending moment is maximum at the location of this pin. And what pin? This is an external pin. the bending moment is not necessarily zero. The support as such doesn't applies any external moment. So these three pins have to be differentiated from each other. Forces on this, which is I think, let me denote them P, P, and P. So the middle thing, there's no force. I think 10 kilonewtons. You have P, P. Here you have a P, P. Now always with superposition. First, I can consider the vertical forces, and in the second case, I can consider the horizontal forces. So in the first case, let me consider only the vertical forces. And in the second case, let me consider only the horizontal forces. Are you aware of symmetric structures subjected to symmetric loading and anti-symmetric loading?
Yes, sir.
Yes. So the structure is symmetric. It has two planes of symmetry, as you can see. This is one plane of symmetry. That is, if you remove the loads, these two are mirror images, right? About this y-axis, let me call this y-axis and x-axis. About the y plane, it is symmetric. If you put a mirror, the structure looks exactly the same. And about the x also, it is symmetric. Here, so the structure is symmetric. Let me put this structure is symmetric. The structure is symmetric. And let me call this case A, and let me call this case B. So whatever bending moment or reactions I get here, we can add them with this. So that's basically the principle of superposition. So if you see in A, the loads are also symmetric. So if you draw a line here, you can see the left and right look exactly the same. So A, the loads are symmetric. In B, loads are anti-symmetric. So what do we mean by anti-symmetric? If you cut the structure here, half of it looks something like this. You have a force P. Mirror here and reconstruct the rest of the structure. You have something like this. So this corresponds to symmetric loading. But what is different here? This P is replaced with minus P. So only the direction of P is changed like this. So it from the other side, if you look, say this, I'm looking at this half from back side of the structure. What does that look like? It looks like this. This is not the case. The given case is this. So if I look from the back side of the structure, you have a P directed towards the support. So these are, if you look at, let me remove this right now. So if you look at this half and this half, everything is the same, except that the load alone is reversed. So, and your line of symmetry, you're replacing this structure with this structure. So what does this mean? The load is reversed. So you say the loads are anti-symmetric. Whenever a structure is symmetric, what are the conditions? What are the conditions for a symmetric structure? So this is the plane of symmetry. Certain zero along the plane of symmetry, and that is very important. That is very useful while solving.
Shear force is
So,
zero, sir.
it,
Along with planes.
yes, it is zero, and one more thing is zero. What is it? Reason why shear force is zero, right? So you have, let us consider the symmetric case. So if I model the structure, I have a force P here, and I have a force P by 2 here, and this is a plane of symmetry. And we have, in general, you can expose both the horizontal and the vertical. You can expose both the horizontal and the vertical forces, which means you have, let us call this H1, H2, V1, sorry, V2 and V1. where V1, V2 are the shear forces. So okay, we need to be a little careful. It's not exactly the shear to this beam, it is the vertical force, right? So the correct way to say that is, we'll see. So is this symmetric? So if the structure is symmetric, it means if I look from the other side, I should see the same thing, right? If I look from the other side, the structure looks something like this. But from the back side, the loads are the same, P/2. And then, so this, sorry. So on the other, and on the other half of this structure, you have something like this. So if V1 is upwards on this half, V1 has to be downwards. V2, and the horizontal forces are in the other direction, H1, H2. And you have the same loading, P and T/2. If you disregard the internal forces, we saw that this is a mirror image, right? So this is just the mirror image. But in one case, when it is, you see from the back side of this, it is exactly this, which means in case when you subject this half of the structure to P and T/2, you have an upward vertical upward force. But on the other half, although the loading conditions are identical, you have a downward force. These two have, so basically the loading is the same. So which means this upward force has to be equal to the downward force. So equal to 0. If you have any other say it is 2 or something, 2 cannot be equal to -2. Case where quantity is equal to its negative is when it is 0. Is the tangential forces along the line of symmetry, along plane of symmetry, forces tangential to the plane are 0. Forces tangential to the plane are 0. And the other condition, the displacements normal to the plane are 0. You can also see that easily. Suppose this point displaces like this. Suppose it displaces by u here. It means in the other half it has to displace, if it is symmetric, it has to displace u to the left. But this point cannot move left and right at the same. This is the same point, so it cannot move left and right simultaneously. If it has to, then u has to be equal to 0. Since you have considered a vertical plane, the tangential forces are the vertical forces, and the displacements and normal displacements are the horizontal displacements. And if you consider a horizontal plane, it is the opposite. So these are the conditions for a plane of symmetry. And what is it for a plane of antisymmetry? Along a plane of antisymmetry, it is just the complementary conditions. So suppose consider case B. You have a force P here. So again, expose both. And the other half has got drawing the other half from the other side, right? So the other half has just got the load reversed. Right? You can see here the load is acting towards the support. Everything else is symmetric. So if you see the structure from back side, that is, you just flip the structure in 3D, it looks something like this. Load acting towards. And so what do we expect? You have just reversed the load, which means the these things have to change, right? So this has to be downwards and this has to be leftwards. So these are consistent. The verticals, and if you put them together, you should get 0 internal forces. That is the other condition, right? So from the condition of anti-symmetry, you see that the internal forces have to flip their sign in these two, but these two are parts of the same structure. Join them together, they must have the same. The internal forces must vanish. So if you say V1, V2, and this is just V1, V2 in the other direction, if you put them, they will vanish. But what about this, the horizontal forces, H1, H2, H1 and H2? If you put them together, at this point, it becomes 2H1, right? So here it is directed towards the right support, right? And here also it is directed towards the right support. So this is the point R, this is the point S. So if you join them together, it becomes 2H1, but 2H1 has to be equal to 0 by Newton's third law. You cannot have unbalanced forces, unbalanced internal forces. Therefore, the horizontal forces should be equal to 0. So therefore, forces normal to the plane are 0, and the displacements tangential to the plane are 0. So this is a very powerful tool. This, along with the principle of superposition, simplifies a lot, large number of problems. So given this, finding the reaction in the second structure is just one step. So let me draw the second structure, the free body diagram of half of this. These are all pin connected. Here you have an internal pin. I'm not putting that. This is a symmetry, and along plane of anti-symmetry. Along the plane of anti-symmetry, what does it mean? Forces normal to the plane are 0 and the displacements tangential are 0. So what is the best thing that I can put here? I can put a roller. You agree? So this will not have any there will not be any horizontal forces, and there will not be any tangential displacements. And here there will be both, because that is, so here we have P acting here, and right. So this is R, and the other half of the structure is something like this. So it is anti-symmetric. You have acting this towards the right, which means if this is the horizontal force, this is the vertical force here. What will be the horizontal force here? It is anti-symmetric, so it will just be flipped. So it will be in this direction. If it is symmetric, both will be directed towards the plane of symmetry. Since it is anti-symmetric, one of the reactions is towards the plane of symmetry, and the other reaction is away from the plane of symmetry. Just exactly similar to the forces. Here the forces towards the plane of symmetry, forces away from the plane of symmetry. So if you see what is H is equal to minus P, right? Because here there is no horizontal force, here there is no horizontal force. This force is vertical, and the question is to find only the horizontal forces. So you got from this loading, H is equal to minus P. So if I draw the correct sign convention, P, and here it is a compressive force of P. Done. So from part B, we are getting reaction, the horizontal reaction at S is equal to P towards the left. Now let us look. In part A, you have this, where is this? This one. Again, we can draw only half the structure. So in part A, you have this. Here the normal displacements and the tangential forces are 0. So you put a roller like this. Now another thing to note is here we are having pin connected, so I'm putting this hinged roller. In general, the moment also has to transform according to the symmetry conditions. So if you have a plane of symmetry, the moment need not be 0, because along a plane of symmetry, if you reflect the moment, it becomes something like this, and they both add up to 0. So those will be retimed, and along a plane of symmetry, you need to put a guided roller. So remember that you need to put a guided roller. Since here they are known to be pin connected, I'm putting hinged with roller. So again, these two are the unknown reactions here. Let us call this HR. On the other half of the structure, what do we have? It is also directed towards the plane of symmetry. So you have HS. And you have some vertical force. Now again, this cannot sustain any vertical force. Here you have P, here you have P by 2. and on the other half you have another P by 2. So the total force becomes P. So what is the vertical force here? It is just 3P by 2. But now what is the static indeterminacy of this structure? Let us see. So you have two reactions. You have 1, 2, 3, 4 members. So 4 into 3 is 12 unknowns. Total, no, not two reactions. You have another two reactions. So two reactions from the left and another two reactions. So you have 16 unknowns, and the equations, number of equations you have is 1, 2, 3, 4. 4 into 3 plus you have two internal hinges. Sorry, 1, 2. Yeah, two internal hinges. So that is about. Wait, something is wrong. So you have 16 unknowns and uh, 14 equations. So this is 1, 2, 3, 4. Right, we need to be careful. So you have 1, 2, 3, 4, and you have another hinge here. So plus two pin forces. So there are totally 12 unknowns plus 6. So it comes to about 18 unknowns. And the number of equations, if you see 1, 2, 3, 4, 4 threes are, you have 12 plus two equations coming from the internal hinges. And you have 14 equations. In addition, you know that um, or rather, let us so you have so let us eliminate the vertical ones, right? So directly we can eliminate the vertical forces. So this reaction is known. So you can get rid of one more unknown. So you have, let us list the unknowns. That is the best way to do it. So you have, let us draw the free body diagrams. This is one member. This is one member. This is another member. And let all the unknowns on this. So you have the horizontal reaction at R, vertical reaction at R. This is a pin connected joint. And you know the bending moment is 0 here. So here, what are the unknowns? This transmits only forces and no moments. So here, let us call them IY, IX. Here, LY, LX. Here, they are just equal and opposite. And here also, it is just equal and opposite. I'm not writing them. Here, the unknowns. Here, so this, at this point, we have the pin forces. And this pin is N. So these pin forces are NX, NY. And here you have the pin forces, opposite, equal and opposite. So I am not listing them. So this point and this point are these 2 points lying along the lines of symmetry. We know the horizontal force. So here I have, this is M or LQM, right? So this is QX and this is JX. That's all. So total number of are 1, 2, 3, 4, 5, 6, 7. So in this we have 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 unknowns. And for each of these bodies, we have 3 equations of equilibrium. So 3 into 9 equations. And therefore, and if you know all the conditions, all the conditions, you can determine the internal force. So you have only the degree of static indeterminacy is 1. So by symmetry boundary condition, we have reduced the degree of static indeterminacy to 1. So what is, you need to consider redundant forces. So what I would say is, let us solve the problem first. Whenever you are unable to solve the problem as it is, because you need to draw the bending moment for all of and then enforce conditions. So let us see how to simplify, and that is the solution that is available everywhere in the internet. So what they have assumed is, which is an unsaid assumption, that this is pin connected. So, but that is not actually in the question. So the correct way to treat it is what we have done. But somehow they accepted in gate is also that if you assume this is pin connected, then it is solvable in the time frame that is given in a gate. Otherwise, it takes time. So let us solve that question first. So that part is something like this, right? So this is assumed to be pin connected. So let us treat this as our primary method of consistent deformation. So if this is our primary structure, what is the structure? Redundant structure. So when I put a pin here, what is that I'm releasing the moment at this frame joint. So like in my redundant structure subjected to redundant forces, I need to indicate the moment. And because of symmetry, not symmetry, this is an internal bending moment, so it has to be equal and opposite. So let me denote that by, let me denote it by sagging moment. It has to be equal and opposite because it is an internal force. And primary structure is subjected to the loadings P and P by 2. And both of them have got the same boundary conditions. This is one and this is the other. And now solving the primary structure is very simple. So a widely accepted solution for this is use the principle of virtual work. You can use as well because this is statically determinate. We have removed one redundant, so this is statically determinate. So you can always the diagram of all these bodies and get the pin forces, the reactions. But when a large number of members connected and the kinematic degrees of freedom are less, the principle of virtual work becomes handy. So let us see how to do it. Now, so again, this point we need to be careful. So the principle of virtual work is that the net work done by the external forces is equal to the net work done by the forces. So the correct statement of principle of virtual work, when subjected to an admissible virtual displacement field, right? So be very careful. The net work done by the system of external forces, the net virtual work done by the external forces should be equal to the net virtual work done by the internal forces subjected to a kinematically admissible displacement field. What do we say by kinematically admissible displacement? It means it has to be consistent with the boundary conditions and the connections in the problem. For example, cannot assume a displacement field in which this pin connection is violated or these boundary conditions are violated. Displacement field like this. This is what principle of virtual work states. Now, if I want to find an unknown force, to determine an unknown force, or we use the principle of virtual displacements. And this holds only static. Okay, we'll come to it. So we'll use the principle of virtual displacements. So if here this problem, I'm interested in the horizontal reaction here, right? And of course, it is the same in the other also. So I want to find out the horizontal reaction here. So let me denote that by this. So if I want to find out the now I'm considering a virtual displacement field. So this I'm not disturbing. I want to find out the force here. If I want to use the virtual work principle, that force has to do some work, right? If I'm interested in a reaction, you know that reactions don't do any work because that where they are does not move as the forms. But I want to find out the reaction itself. I want to allow some movement of that point. So that is a virtual displacement. That is not actually, that's not a real virtual displacement. So let me relax this boundary condition like this, and let me move point by a virtual displacement delta u. So this is a virtual displacement. As a result, this is how the structure deforms. Again, this cannot move. This can move vertically. So let me. So it becomes this angle, which is initially at some other 90 degrees. This reduces. So suppose this angle is theta. These are pin connected, and the load is acting here, here, and here. Now, in doing so, here there is always a horizontal reaction. Let us call it HR. What is the work done by HR in moving through this? So the virtual done by the external forces. Let us find out the total work done by the external forces is HR is towards the right, and okay, fine. So I should the other way. Let me displace it to the right so that it becomes something like this. I don't want to deal with negative signs. Nothing is wrong in doing that. So this is what we have, and I'm displacing it to the right, because we want to deal with quantities. Let us say this is delta u, and this is coming here. The support is moved here. And let me draw the deformed shape. And it is to be kinematically admissible deformation, which means it has to be like this. This angle increases. For this angle also increases. It becomes something like this. This moves up. So here we have P. Here you have P by 2. And here HR is acting. So the net force, the total is HR delta U. And here is delta theta. The change in angle is delta theta. So this is theta plus delta theta. So this point has risen by some amount. What is that amount? Well, the virtual displacements are infinitesimal. So if you rotate this by delta theta, this goes up by uh, uh, this distance. You can take it as so if this rotates by theta, this totally this length tan theta plus delta theta minus this length tan theta. So to a first approximation, you can take the rotate. So because of this rotation, you have because of a rotation by delta theta, and if the length of this member is L, the arc length is L delta theta. But you are interested only in its vertical component. So it is and it is going up, the load is acting down. So it is minus P L delta theta sine theta. And what about here? Here also, if this has gone up by theta, this rotates by the same angle, right? So you're pushing it to the right, and the load is always acting there. So this moves up. So this rotates by theta, sorry, delta theta. So here the same virtual displacements are. So this also rotates by delta theta because of the mechanism. Again, what is this moves? It is also minus. So the force is P by 2. Force is acting downwards. The displacement is up, so the work done is negative. Into so again this bar rotates by about this point. This bar rotates by the total length is 2L. but you are in, this is the center of rotation. So the radius is L, and the rotation is delta theta. Again, you have the same thing, delta theta sine theta. Now, what is the internal virtual work done? So here you need to be very careful. Structure is already statically determinate. When I remove one of the support reactions, the structure becomes a mechanism. It cannot safely transfer loads any longer. So when I remove the horizontal reaction here, it becomes a mechanism, which means uh, there are no internal forces. It doesn't deform. So if a structure deforms, if you have an assembly of components, when you subject it to the loading, it has to deform, generate internal forces, and resist the applied force. When all the internal forces, when it is a mechanism, it accelerates. It cannot deform. So when it doesn't deform, by Hooke's law, there is no stress, so there is no internal force. And if there are no internal forces, the internal virtual work is zero. Now, what is delta U that we need to see? So this has rotated by delta theta when about this point. So, uh, so if you take now take this, so if you move this by, so you have something like this, and the deformed shape is, so let this be the deformed shape. It is something like this. About a certain point, this has moved. This has moved. We need to find this delta U in terms of delta theta. So that finally solves our problem. So how much is this movement? So if this rotates by delta theta, and considering this as the point of, so this is so let us, this has rotated by delta theta. Therefore, this point has moved. This is a point of zero translation, right? So here the displacement is zero. This entire thing has rotated by delta will be 2L delta theta, right? Here the 2L delta theta, and we are interested only in the horizontal component. So this is 2L delta theta cos theta. And here about this point, this has rotated by uh, you have from this point to this point, you have L delta theta cos theta. So the net horizontal displacement is 3L. So the net horizontal displacement, horizontal virtual displacement. So I hope you get the point. This has rotated by delta theta. Therefore, this moves to the right by 2L. But with this point taken as the reference, this has rotated by delta theta, which means this has moved by L delta theta perpendicularly. But if you take the horizontal component, it's L delta. So the net horizontal virtual displacement equal to 2L delta theta cos theta plus theta cos theta. So this is nothing but 3 delta theta cos theta. Now just rearrange the equation. So we have work done is equal to the 0. So the horizontal reaction at multiplied by 3 3L delta 3L delta theta cos theta minus L delta theta sin theta is equal to 0. So delta theta is an arbitrary virtual displacement. It can be any value. You can take it to be non-zero and you can cancel it out. L gets cancelled. So the horizontal reaction is nothing but P by 2 tan theta. What is tan theta here? So in the given problem, I think they are 1 meter and 1 meter. So this is 1 meter, this is 1 meter. So tan theta is 1. Tan theta is 1. So the horizontal reaction at R due to the given loading is P by 2. So what is the net? The net. So from where did we do the decomposition of structure? So here from the point B, from the structure B, we have at HS. So this is towards the right, right? This is what we assume. We get a positive sign, so it is assumed direction is correct. So HS is from the P to the left side, and from the structure A, we got HR is equal to P by 2 to the right side, which means HS is P by 2 to the left side because it is symmetric. Now, what is the total net reaction at S? Sorry, let us use some other. The net reaction at S. So this is from the structure B. This is from the structure A. It is towards the left side. So P plus P by 2, which is 3P by 2. So the correct answer to the question is 15. No, that is not the correct answer, unfortunately. So if that hinge is there, if you solve the primary structure, you get the reaction, horizontal reaction at S as 15 kilonewtons, which is 3P by 2. But unfortunately, that is the accepted answer, but that is not true. You need to superpose with another path, which is the redundant structure. Now let us solve this. So although the accepted answer in gate is 15, but that's not the right answer, unfortunately. So let us. So is that okay? Until this point, you have any doubts in virtual work or anything else?
No, sir. Understood,
Okay.
sir.
So like, was this? Yes. Okay. Okay. Uh, Now look at the redundant structure. That is simpler. So you have moments acting this way, and it is symmetric about this. So you don't need to do it 2 times. You just solve this one, right? You just get the bending moment diagram basically. So here in the redundant structure, so in the redundant structure, let us solve for this. If you draw the bending moments everywhere, let us look only at this one and this one. So these are like this. It is pin connected here. So here you have a bending moment of, so you have a bending moment of M here and 0 here. So directly, this is the bending moment diagram. So this is symmetric. So this has the same bending moment diagram. And this is pin connected. So here you should have 0 bending moment. Here you should have 0 bending moment. And the middle you have some maximum bending moment. So it is plus or minus, we don't know. But let us just take this is, and there are no forces in between. So the bending moment diagram of the redundant structure is like this. So, but what are the actual magnitudes that you will get directly? So here you have a shear force. Here in this primary structure, you need to have, so the reaction here has to be 0, right? Because the redundant structure, we have only internal forces. The reactions have to be 0, right? So this this member has got 0 normal force. Uh, Let me put it this way. So here you have 2 members connected like this, and you have a pin, and this is 90 degrees. So the normal force in this member is the shear force in this member, and the shear force in this member is the normal force in this member. The net force on the pin is 0. So that is the idea. So here you have some normal force and you have some shear force. Let me denote it by like this, shear force. So here, what is the normal force? It is V. And what is the shear force? It is N, because they're perpendicular to each other. Right. So this is V, this is N. And coming to this point, so this is N, this is V. Again, this is connected perpendicularly. So that's a simplification. So the shear force acts as the normal force here, and the normal force becomes the shear force here. Here the shear forces are not continuous. You can draw up to this point. Again, actually, this is also not continuous. So here there are some pin forces. Let us, you need to find them. Let us call these. Mm, this has to be N pin, right? So this is NX, NY, and here you have opposite direction, NX, NY, and then what else? Yeah, so this point is connected to this point. So here you again have the normal force becomes the shear force. and shear force becomes the normal force. This side you need to determine depending on this. You just use equilibrium, so you get the two other components. So, and then you can also always movement diagram. The maximum is at the center. Once you get, so if you know this is the normal force, what is the maximum value is n times L. So this distance is L. This is the normal force. If you take, if you cut anywhere, it is Nx. So this is NL. And here also it is some NL. Positive or negative that you can determine. So this is NL. So we have got everything in terms of the normal force. The only thing that we need to determine here is the magnitude of the normal force as it is. So you have, for that you can use the equilibrium of the structure. So again, here the shear force has to be 0, which means, right. So where is this? Yeah. So in the redundant structure, these should have no forces. Therefore, the normal, both the normal force and shear force and the bending moment on coming onto this point is 0. We can't say in general. So up to this point, they have got some. So at this point, the normal shear force and the bending moment are 0 because there's only one member connected. So these numbers are actually, so when you apply a certain moment here, this is the primary structure. This part of the structure is actually unstressed. So here you have no normal force, no shear force, and no bending moment. So here you need to, yeah. So here you don't have any reactions both in both of these points. You can directly solve for the given this as the condition, you can find out what should these values actually be. So if you do that, if you solve for that, you get the pin forces you can get. So here the unknowns are N, B, and you enforce moment equilibrium here. So these two are directed at this point, and here you have a which is not which is away from this point. So this member, so this is kind of, so you're hinging it here. So you're hinging it here. You're hinging it here. You have a member like this. You have a hinge here, and you have something here. Now, at this point, if you have forces like this, they must add up to 0. But there are no external forces. If you look at this redundant structure, you have got right. You can't do that. So this. Okay, I think. So this redundant structure statically determinate. You can enforce this M, and reactions and get the bending moment diagram. So from this you find out what should be. So from this bending moments of all members. Again, from this you can solve for the bending moments of all. Then you use Castigliano's theorem. So superpose both. So superpose whatever bending moments you're getting. So make a list of members. I'll do it. I'll definitely write it down on paper and send it. Make member versus the bending moment as a function of x, and then which is coming from the primary structure, which is coming from the redundant structure, and write these down. So the net bending moment as a function of x you get. Then in the members you need to find this quantity, which is the strain energy. So m square by EI. Integral m square 0 to L m square by EI. So that will be a certain function of m. So m is the unknown redundant force. This will be a certain function of m. Then use Castigliano's second theorem, which says the rotation is nothing but the the displacement at the load point is nothing but the partial derivative of the complementary strain in respect to the unknown force. So here the relative rotation between the two should be the partial of the strain energy, which is a function of m. So add these up. This with respect to now what should be the rotation, because it is a rigid point, is equal to 0. From this value of m, and once you have all the horizontal reactions and everything in terms of m, substituted and then superpose with the solution that we got for the primary structure. So from the primary structure, we got there to be p by 2, and definite structure you will get something as a function of m, and you know what m is. So superpose that will give you the net horizontal force for the symmetric case. Now add it up with whatever you get from the unsymmetric case, which is p. So that is the net. That is the total reaction at the point r. So we start. Temperature joint, it is quite difficult. So you right. So sorry. Yeah. So I was saying that this with degree of static indeterminacy too, it is a difficult problem with so many members. So unless this is mentioned, it is free to rotate. You cannot assume it to be a hinge. But somehow the accepted answer is 15. But the correct solution to this is that m has to be determined by the method of consistent deformation. So
Okay, sir.
go to shear center because shear center, because you had asked it last time. So this in shear center, the key, like, when you have a beam, usually this is the kind of cross sections you would have seen in your UG. What problem with my internet?
Sir, am I audible?
Hello.
Sir,
Is it audible?
yes, sir. Yes, sir, your voice is audible, but sometimes there is a break in between, and also there is a lag between the screen and the voice because it was raining here and my network connectivity is poor. Sir, but I could able to listen and see, but the connectivity is poor, sir.
Okay. It also rain here in Bangalore. There's also it is rainy here also. Maybe then we should. I'll do one thing. I'll record it and upload it separately. The shear center, because again we don't want to. Exam is close. I don't want to delay it any further. I will record it in my system. Upload it. Is that okay? That will not have any lag.
Okay, sir.
Okay. Yeah. So sorry for today. It was unexpected.
No problem, sir.
I'll ensure this doesn't. Yeah. So I need to upload about three things. One is the shear centered part. The other is this problem in structural analysis. So for gate, I think this is enough. 15 is fine, but the correct concrete. There's an older session which I can. Okay, I think I have to stop.
Yes, sir. Yes, sir. I saw that, sir, that
So
RCC on older session on RCC, sir.
so in addition to that, if you which are the particular topics you want, if you say, I can narrow it further, because RCC is a little big area. So, and it has some other weightage. I could say mostly they ask some moment of resistance and shear stir up design. These are the two commonly asked questions. Otherwise, sometimes they ask something from the code minimum steel reinforcement or minimum torsion reinforcement, something like that. So maybe only problems only session will be okay, right? If you want some concepts, I'll explain along with the problems, but we'll mainly focus on problems.
Yes, sir. We can focus on problems, sir. But for RCC, it's fine, sir.
Thank you.
I looked at the older sessions, sir. It's fine, sir. Uh,
Okay.
if any topic is required, I will post it in
Okay.
Google Groups.
Okay. Sure. Okay. Thanks for joining, and
Thank you, sir.
thank you. I'll end this.